Excellent. Okay, so we're all back for our lecture for today, and then I guess we'll take a pause for the rest of the week, and we'll see each other on Monday. So I hope y'all have all been making progress on the challenge that I've given to you. Has it been pretty insightful trying to actually see the little micro bits of C that we've gone over for the last several lectures and seeing how well you can actually execute on them to try to translate something that's a relatively simple Java code base into a C code base? It's not trivial, right? No, yeah. So, but I think after working on this application, it's really going to give you the chops you need to feel much more confident in C for all the labs that we're going to go ahead and move on, moving forward. And so with that said, talking about labs, we also have the introductory lab that's available through AutoLab, right? So if you go to AutoLab, you should see the documentation for that. I think I have the lab resources available through GitHub. And so that lab does a great job of kind of walking you through, kind of playing around with a little bit of C code, but also enforcing upon you an understanding about how we go from our text file, which represents our source code, to an executable object file that allows us to treat it as an application that actually runs on our system. So for today's lecture, I really want to focus in and get a understanding of that kind of trail, that journey that goes from authoring a C code file to the point where it can actually execute on our computer system. So we'll do a little bit of implementation inside this class, but this one might be a little bit more slide driven simply because of the content we have to cover. It's a little bit more for a more abstract presentation, but we'll try to dip into the shell and see what we can do with the shell when it makes sense. Let me get the presentation slides up on here. I see what's happening here. I need to put an HDMI cable to my computer for the class to see. Set up an adapter, but I did not do this. And then when it comes time to go ahead and turn in your lab, you should just be able to turn it on AutoLab. The nice thing about AutoLab is it's an assessment tool. So as soon as you turn in your class assignments there, it'll, at least with the labs, not for the challenge that I gave to you, that's something that that'll be assessed personally by me. But in terms of the labs will be automatically graded and assessed, and then you'll get your feedback right away. And you can resubmit as many times as you want. So there's no reason why you can't get full points for the labs if you're vigilant enough to get those points. It's not like once you turn in your grade, that's what you get. That's just what you get for that instance. And that'll be true for all the labs as we move forward. Okay, so let's take a quick tour of computer systems. And so this content is actually grabbed from the first chapter of the textbook, which you should have a PDF or ebook version of through the university's access portal. Okay, so let's start by defining what we want to do. So in today's lecture, we're going to introduce our major concepts for a computer system, because that's what this class is really geared to have you understand. So at this time, you understand how to author Java code, and now at this point, some C code. You know how to compile it, you know how to run it, but really everything in between is probably still magic to you. Can you close that door for me? And so one of the motivations behind this class is to kind of unveil that curtain of what happens inside the system, which is really going to prepare you for your operating systems class, which is going to go one level lower than this class. So what we're going to do for today's lecture is just kind of dip into the life cycle of the Hello World program, the simplest program to write, right? This is usually the program that every beginning developer learns to author. regardless of the language. In fact, as you learn a new language, usually this is the first thing you learn to do in that new language. Okay, this chapter is separated into multiple parts. This is just a quick overview, so you know. I don't know if we've done this before, but we've defined computer systems in particular. Why don't we actually apply a hardened definition to that in case we haven't done that yet? So a computer system consists of both hardware and software, and they both have to work together in order for our application programs to execute. So we're going to look at the software perspective in part of this class, and then we're going to look at the role of the hardware perspective and see how those two things come together. Okay, so the learning objectives, not just for this chapter, but for this course entirely, is going to be to have a greater understanding of numerical precision. So you want to be able to understand and prevent numerical errors due to your due to the way the system goes ahead and represents numbers. It'll allow you for code optimization. So if you know how the underlying system works, then you can optimize the implementation of your C code to take advantage of that. Security and procedure calls are going to be a consideration, simply because if you understand how vulnerable software is made, you can protect your software so it's not vulnerable to things like buffer overflow vulnerabilities. And I think we've kind of seen some of those, right? In some of the slide presentations, when we're looking at scanf, we saw why we don't want to use scanf for being able to grab text necessarily, because it allows you to overwrite your memory with new values. Linking and debugging, this is going to be part of our compilation tooling chain that we're going to look at. And so we'll know if we have issues in terms of how our code is linking together, or if we're having issues with our code executing, we're going to learn how to use the debugger. We're going to learn how the linker works so that you'll be more primed and ready to debug code. We'll do some actual system programming projects. One of the labs, probably one of the more infamous labs that you've heard about in this class, is that you'll actually create your own Unix shell. So the shell application is what you used in Java 1 and Java 2 to go ahead and compile and execute your Java applications, right? That it allows you to launch applications. It has a lot of different utility applications in there. We're going to look at building a tiny shell over the course in the latter part of this semester. And then finally, process management. So all of our running applications in memory are effectively processes that are managed by the kernel, by the OS. We're going to understand what that means. Okay, so as I stated earlier, every program, including our Hello application, relies on the entire computer system in order to execute. So if you want to know how software works in a computer, we have to know what part of it is driven by the software ecosystem and what part of it is driven by the hardware ecosystem. So we want to understand what happens and why when we run our applications inside of our system. And so we can think of it, if we go to trace the lifetime, at least just from the software perspective, if we abstract away the hardware, we can say it happens in 6 different stages. You have a creation stage, a compilation stage, a loading stage, an execution stage, an output stage, and the termination stage. So during the creation period, effectively what you're doing is you're going to have your program created, written, and saved as a source file. You usually use a text editor to do this, and it stores it as a file on your system. Then you have a compilation phase. So in this phase, you have your source file, which can then be compiled into an executable format by a compiler application. Then you have your loading phase. The loading phase takes your executable, loads it into memory by the operating system. During execution, the program launches, executes the instructions by the system CPU. The output of our hello prints the message to the console through the output stream. So our system supports input streams and output streams. So the results get directed to the output stream, and that's where we get our message onto our display. And then finally, when the application is done, you have a termination phase where it will then, the program exits out, and then all of the allocated memory that was reserved for that application is released and now re-available to the system at large. So quick bird's eye view, that's what happens software perspective when we run our application. Sure, yeah, no choice. Okay. So let's kind of step through each of these one by one. We start with this application, right? So here we have our preprocessor directive, hashtag include standard out the header file, which is going to give us access to whatever functions are declared in there. We're going to create a main function, which is going to be our launch point of our application. Inside there, we're going to invoke the printf, which is what we imported from the standard input output library. And so we'll send to it this string, hello world. So it's important to understand when we alter this in our text editor, the text editor is displaying this as a set of characters that are visible to us. We save that in what's called a source file. A source file, when we save that by the text editor, saves it simply as a sequence of bits that encode our instructions that the computer then can translate. So what we see as text is translated into effectively a binary sequence, but this isn't necessarily a binary file. We'll call this a text file because the encoding of it uses a ASCII encoding. So from characters to bytes, our text characters from our L06 are encoded using the ASCII values. They are it allows us to have a readable code, then be converted into a byte-sized integer-based format so that our system can process on it. Right? Our system can't process alphanumeric languages, right? So everything has to be converted into binary sequences. Okay, so let's take and prove this to you, right? So I'm saying this, you can trust me. We actually have some system tools to see how the text of a source code file is actually mapped to a set of binary sequences or binary characters. We're going to actually look at two different command line utilities to actually prove this. We're going to look at one that's called XXD, which is a utility that allows us to create a hex dump. So XXD, that's effectively XX is for hexadecimal value, the D is for dump. And so it'll allow us to pass in a file, our hello.c file. And so these flags that we're going to send to our command line utility, so we can send a flag, it's like a property to the application. Usually we start that or preface it with a dash, so dash G will group the output in single bytes. Because the encoding for an ASCII character for a car is 1 byte. And then we're going to go ahead and display that out. And what we're going to see, the output B is exactly what you see here on side this slide. You're going to see the first column is the set of memory addresses. And the second is going to be the individual ASCII encodings in hexadecimal value for each of the characters that represent our source code file, our text file. All of our source code files, we call those source code files, they're effectively text files though. So no different than a .txt. But the extension is used so that when we feed it to a compiler, it knows how to parse it and translate that into something that's going to be executable. Here in this, so in the second column is going to be the hexadecimal representation of our hello world source code file. And then here, this third column represents the retranslated characters so that we can map one-to-one what they are. Now, like I said, ASCII typically represents each character to an integer value. So the first way that I showed you that we can inspect this is to show off the hexadecimal representation of each of the characters in our text file. If we actually want to see the integer value, which lines up more closely with the ASCII standard, because it uses base 10, we can do that with XOD. So O is octal. So this is allowing us to do an octal dump. But in fact, the octal dump utility allows us to either express it as an octal set of values, a hexadecimal set of values, or a decimal set of values. So the flag of -T allows me to define what type of output I want. And then I can then give the output based off of here, I'm using D short for, or lowercase d short for decimal ints, and uppercase C to correspond with its ASCII characters. And then I give it also the input file by which I want to display what the encoding contents looks like from my underlying system. Now I can run these. I actually have this set up where I can grab this. This is just a text field. I can put this into my system in favor of time because we have a lot to get through. I will not do that because I'm showing you the output here. So all I would do by actually compiling and showing you this is, I think, waste a minute or two. So I will trust, you will have to trust that this produces this output, but I will share these slides with you and you can test on your own system. You can make a hello world. You can run these command utilities and see this is going to be the exact type of output that I'm going to get. And in fact, I'm going to now match this up. Using these integer ASCII values, I can then do a one-to-one mapping and see, hey, yeah, that source code file that I authored in my text editor has a direct binary representation using this ASCII standard where I can translate the binary back to text or the text back to binary. So every text file that we have in our system, this is how it saves. Now, I want to make a little distinction here. I want to distinguish the fact of what's normally referred to as a text file versus a binary file. And so for those of you who have gone through Java 2, you probably used a lot of the libraries for input stream and output stream, and there's probably a lot of system calls that allowed you to treat things based off of text streams and binary streams, right? Was that something that y'all covered inside of Java 2? The different formatting that your input and output streams could have, whether it was binary data that was coming through the stream or text. Yeah, okay, perfect. So that metaphor goes deeper than Java's set of libraries, the standard libraries. It goes all the way down to the system level. So typically, these files that are encoded in ASCII directly, so that when we understand the context of that file, we apply the ASCII translation from the binary 1-bit sequence back into the characters, then we can take any of those files and make them back into characters. Those are always referred to as text files. The moment you have a file, though, that includes non-text data, then the entire file is considered a binary file because it has portions that aren't designed to be translated into characters. It's not designed to be human readable. Most files that are on your system are going to be binary files, right? So like a JPEG is a binary file. You apply the JPEG context to parse it into some image processing application so you can display it. Same with PNG, same with our Java source code files or our C source code files. But typically, we can categorize the files on our system as either those that are binary, which are non-text or include non-text data, and those that are text files, which includes exclusively text-encoded binary sequences. Okay, so now that we've established how our source code file is actually stored into our system, let me make a very blanket statement. All the information in our computer system, including the contents of the disk file, including the programs that are currently in memory, including the data that's currently in memory, and including any data that's transferred over the wire or through networks, is represented in binary sequences. That's what we process on. Everything that we have internal to our system is binary. It's in a sequence of bits. So that means everything from the system's perspective looks exactly alike. It's just a sequence of zeros and ones. The way that we're able to intelligently parse it into meaningful things is because then we also have to apply context to the binary sequences. So we distinguish our different data objects, such as an integer, a floating point number, a character string, or instruction, a machine instruction that actually gets executed based off of the context we provide, because they can all have the same sequence of bytes. It's just when we parse that sequence of bytes as an int versus a float, they now mean different things. They translate into different things. Okay, now let's start walking through. Now that we've talked about how we've now stored our source code file for Hello World into our system, let's move on to the compilation system. So we have authored our text file. The next phase is we have to compile it into something that's executable. We use an application for that. So first of all, we use an application to even create our text file and to author the characters into binary sequences. Usually we call that a text editor or a code editor, right? So we use one application to create our source code file. Once we have our source code file, we have to use another program that translates our text file into a different form, which will be primed for our system to start executing it. And this is what our compiler is. So our Hello program begins as a high-level C program because we can read it. It could be understood by a human person. That's what we mean by high-level languages. That's the distinguishable factor between something high-level and low-level. So to run our hello.c on the system, the C statements have to be translated by other programs into sequences of low-level machine language instructions. And so these instructions are then packaged in the form that's called an executable object file. And that's what we can then invoke from our command line and actually execute to get some results from it. So an example of this is we use the GCC compiler driver, which can take our source code file and translate it into an executable object file. But the compilation process actually includes multiple steps. If you've already started in the lab, you're going to see that what those multiple steps were, but we'll kind of step through that in today's class too. So these are going to be the 4 stages of compilation that occurs from our initial C file until we get to the resulting executable file. So we have to go through a preprocessor step. We have to go through a compiler step. We have to go through an assembler step, and we have to go through a linker step. And so here inside of this diagram, you'll see the step name. You'll see inside of parentheses, CPP, CC1, ASLD. This is the alias, the symbolic link towards the utility application that gets run by GCC. So in order to do all of this at once, this is all hidden to us. Like this is the black box that the GCC does to convert our source code into an object, executable object file. Now, each one of these things, the system invokes eternally. And the way it invokes each of these things is with CPP. That goes and does the pre-processing step, which we'll talk about in just a moment, which takes your C file and converts it into an I file. Then your I file is sent to the CC1, the compiler, which turns it into an S file. So here we start with a text file, which is human readable. It's our C code. After this step, we're still going to have a text file, human readable code, but it's going to include everything that the preprocessor directives told it to include. So it's going to effectively nest everything into the one text file. Then it's going to go through the compilation step. That's where it takes our C code and turns it into assembly code. So at this point, if you were to look at this, it's still text file. Assembly is still considered a higher level language in the idea. It's a low high level language, but it's still human readable, right? You can read assembly language. So, but it's the level right above our machine code where we're no longer able to read it, where everything is binary sequenced to the instructions that the CPU will then execute upon. So from the compiler, we'll get a S file, hello.s file, which is going to include the assembly instructions. We can then send that to the assembler, which translates it from assembly into our actual binary machine code. Because again, everything in our system has to eventually resolve to be a binary sequence. And that's going to be our .o file, our object file. And so at this point, this is a binary file. We can no longer read it. And then this gets sent to the linker, which is going to link all the individual object files together. Like, for instance, we might have our hello.o file, which is one object file. And then we'll have our like printf object file, which is in the standard library. Those two have to merge together to create one complete executable application. And once we have that linked set of object files, we can invoke that from our system, actually launch it, and go through that life cycle that we talked about earlier. So here we'll walk through this process so that we can actually see on the slide each one of those steps. We have our pre-processing phase indicated by CPP, which again, in the lab, you will get to execute each one of these phases in isolation and be able to inspect the contents of that file. That's one of the main drivers of the lab, so that you can see what's happening during the compilation phase. So here we'll take our hello.c file, we'll send it to the preprocessor, and now what this is going to do is it's going to take all those directives that start with a hashtag, say for instance the hashtag include, and it's going to replace that with the necessary C code to actually perform that action. So it's simply going to go and insert the program text where we told it to. So this it's a solution that helps us break our code down, and then it allows it to merge and seam it together for us. Then the next phase, after we get this hello.i file, which is all the preprocessor directives being resolved, now we can go through the compiler phase. Because now all of the code is in one file. During the compiler phase, our text file is then converted into another text file, the hello.s file, which translates our C code into one-to-one correspondence to assembly language code. So just an example of actually what our hello world would look like once it's assembled would be inside this panel here. These are the instructions that they would get translated into. Then once we've gone through the compiler phase and we have our assembly code, then we go through the assembler code, translate our assembly set of instructions into the corresponding machine language instructions, which can actually be fed to the CPU to actually encode the actions that we need for Hello World to resolve. And so this is going to create what's called a relocatable object program. It uses the extension .o. And this is where we now move from having a text-based file into a binary file, which encodes our main function, but only our main function. And so what we have to do to get this into an actual executable application then is we have to use the linker to merge our main.o object file with that print.f object file. And once those are merged together, now we have an executable object file that it contains and encapsulates everything necessary for the system to run our code, our Hello World. It's a lot just to compile this into an executable. Okay. So why do you have to understand how this entire compilation system works? Because they're well-solved problems, right? You're never going to build your own compiler. Many years ago, as a computer science student, one of the required classes used to be compiler design. You used to have to build a compiler. That's not something anyone has to do anymore. But there's still benefits for knowing how a compiler works. It allows you to understand how to optimize your own code better. You'll understand how to debug your code, and you'll be able to avoid security holes. Okay, so once we've compiled our code, we can go ahead and run our hello program application. To run the executable file, at least on a Unix system, we can open up a shell. And so that's the application we're going to really focus on over the course of this semester. So the application program that's used for executable files, for launching executable files in a Unix system is, we're going to use a bash shell in particular. There's different flavors of shell, but they're all shells. And so the shell you can think of as a command line interpreter that prints a prompt, waits for you to type a command line, and then performs the command. It's what's usually called the rebel. Because what it does is it reads for your data. It's going to execute whatever the prompt is. It's going to print the result, and then the L is loop. So read, execute, print, loop. Rebel is usually what these applications are referred to. And so sometimes you'll have some scripting languages that have their own rebel built into it. Like, for instance, you can launch Python's rebel, which allows you to feed commands directly into Python and execute it. JavaScript has a rebel. Even Java has a rebel that you can launch and play around with. Let's see. So they load and run the hello pro. So the responsibility, though, is you have one application that we rely on to build your text files to begin with. There's that's our text editor. You have another application that is your compiler that converts your text file into a binary executable file. Then there's another application that we're using to actually launch the executable for it to actually execute, right? So we're using, in the course of running our hello world, 3 different applications. Notice we rely heavily on applications to constantly translate one part of our program into another phase so that it can actually do something. So the recognition is that the shell is not dissimilar from the compiler, which is not dissimilar from the text editor. They all have a role to play towards having us author, compile, and run our applications. Okay, that's it, I think, for the most part with the software component, because we talked about what it took to create a text file. We talked about how to compile it into a binary file. We talked about how we can launch the binary file so that it executes on our system until it finally prints out to the display and then terminates, relinquishing that memory. So done with the software perspective, let's dip our toes now into the hardware perspective on how we rely on our computer system to run our Hello World application. So our computer system, first of all, let's do an autopsy on it. Let's decompose it into its constituent parts that we actually care about in terms of understanding how our applications run on a piece of hardware. So we can isolate and categorize the components we're going to need into 4 main groups: a set of buses, a set of input-output devices, a set of main memory, and a set of processors, or a processor. So this here, I've color-coded in the red our buses. So they run throughout our system. They're a collection of electric conduits, and the responsibility of the buses is to carry bytes of information back and forth between each component. Hence the term bus. It's like a bus line. Our bytes get on one station, right, one port, they get shuttled over to the next, where they're then unloaded. Buses transfer based off of a fixed size of chunks, a fixed size chunks of bytes known as words. So it's very apt if we encode all of our knowledge, all of our concepts as bytes, and a byte is a chunk of 8 bits, and we can combine these bytes to make more expressive things. These more expressive binary things are called words. I'm sure you're already familiar with that from assembly, though, right? The naming usage of bits, bytes, and words, double words. Perfect. I don't know. I'm trying to get feedback, looking at faces and whatnot. Okay, so with that said, the value at the system level of what's defined as a word is not universal. It can be varied system by system. Some system might define their word size as being 4 bytes, 32 bits. Some systems might define their word size as being 8 bytes or 64 bits. If you've ever wondered what the distinction between like Windows 32 versus Windows 64 is, that's all motivated by the definition of how they've defined their word size. That's why some applications might be compatible with one system and not another, right? So our applications could be constrained to the underlying implementation of the hardware system, because it's a hardware consideration. It's a hardware thing. Okay, so here in this graphic, we can see this is our CPU. Let me go back up here before I highlighted it. Here's my CPU. Here's my main memory. Here's my input-output devices. So on the bottom is my input-output devices. On the very right is my main memory. On the very left is the CPU. And kind of like riddled throughout it all is the buses. Okay, so now that we know what the buses are there for, let's talk about what usually attaches to the buses. So let's start at the input-output component of things. That's going to be our devices. That allows our system to connect to the external world. So the purpose of each of these is to transfer information back and forth between the I/O bus and the I/O device. And so these can include things like the USB controller, which we can then have our mouse attached to. It could have our keyboard attached to. It could be our graphics adapter. That's what we put our display to. It could be our disk controller, which is our hard drive, right? All of these things are input-output devices. They might use that data in very different ways, but the underlying data is all just binary sequences. So the drivers that then utilize that input device will then give it the context it needs so that it can display on a monitor, or it could write to a disk file, or it could translate mouse inputs into some kind of meaningful input for us, or keyboard input. Okay, let's move on to main memory. So main memory is going to be this component here. The role of the main memory is as a temporary storage device that holds both the program itself and the data it manipulates while the processor is executing that program. So physical main memory consists of a collection of dynamic random access memory chips. Logically, memory is organized as a linear array of bytes, each with its own unique address, starting at 0. So there's an abstraction. We'll talk more about what this abstraction model is, but we, as software developers, don't need to know the actual physical address of where we need to store our data in. The underlying OS system all is going to abstract that away for us. We'll effectively just have a big heap of memory that we are giving addressable spaces into, and that's where we can go to write and read from. But effectively, all of that abstraction exists on top of those actually memory modules. And then finally, we have our processor. The processor, which we'll typically refer to as a CPU, is the engine that interprets or executes our instructions stored in main memory. The CPU is a word-sized storage device where you have access to registers. And so again, you're probably familiar with being able to access your register space from assembly. And you also have a program counter that tracks where you're at inside of your application. Again, a concept you should be familiar from assembly. A processor repeatedly executes the instructions pointed at the program counter and updates the program counter to point to the next instruction. And so a processor appears to operate according to a very simple set of instruction execution model, which we call the instruction set architecture. That's the set of keywords that you can execute that you're given in assembly. So each one of those things like move, add, sub inside of assembly has a mapping to your instruction set architecture. Yeah, your instructions execute in sequence in a series of steps. The CPU reads the instruction from memory pointed by the program counter. Then the CPU interprets the bits in the instruction. So again, it's a binary sequence, but each binary representation means to do some different action. It's an encoding to send information to some part of the system. So the system uses the ISA to translate a set of bytes into an actual action to execute. We're going to see what this means in just a moment, or if not this class, next class for sure. CPU, then the CPU performs some operation defined by the instruction, and then it updates the program counter to point to the next instruction. So that's kind of like your rebel at the CPU level, where it reads, it evaluates, it prints, and then loops. So the operations, again, interface with the main memory, the register file, and the arithmetic logic unit. So if we were to zoom into the CPU more so, we can see this is our registry files. We have our program counter. We have a memory interface so that we can access things from memory in addition to our register space. And then we have our arithmetic logic unit that allows us to actually start doing transforms, start processing some sets of binary inputs to get resultant binary outputs, right? Now, this zoomed in view, did y'all spend any time talking about inside of assembly? At least kind of remedially? Okay, so if we were to kind of look at the instruction set architecture, just to go ahead and provide an overview, we could break it down into a load, store, operate, and jump actions. Load will copy a byte or a word from main memory into a register. Maybe a keyword for that might be move. Overriding the previous contents of the register. So clearly you need to have an instruction to be able to move data into your registry space. Store, which allows you to copy a byte or a word from the registry space to a location in main memory, overriding the previous contents of whatever was inside of that memory space of main memory. You have operate. This is going to copy the contents of two registers to the ALU to perform some arithmetic operation on two words and store the result in your registry space, overriding whatever the previous contents was there in the registry space. And then finally, jump, which will extract a word from the instruction itself and copy that word to the program counter, overriding the previous value of the program counter. So typically, these are the four actions that a processor can take from our instruction set architecture. And from these, you can build really complex sets of instructions. Okay, so now that we've laid out the atomic components that define our hardware side, let's walk through the life cycle of our Hello World application as it actually executes the hardware perspective as opposed to the software perspective. So here I have a diagram, a directed diagram, so that you could see our starting point to our ending point, at least from steps 1 through 4. So on step 1, which we're going to say is right here, the shell program is waiting for us to type a command, right? So it's waiting for us to prompt it to do something. So it's looking towards this mouse keyboard input-output device. When we type something in the keyboard and hit enter, that's then put into the input stream, right? That input stream connects to this I/O bus. We type the characters .hello at the keyboard. The shell program reads each into a register and stores it in memory. So we type that in, we go into our input-output, we go into our memory interface here, and it stores in memory, and then the shell then loads the executable hello file by executing a sequence of instructions that copies the code and data in the hello object file from the disk to our main memory. So when we get this in here, it goes to our register file, which then goes to our main memory to load this up. So that's the first thing that happens. After that, once we have everything in the main memory here, the data travels directly from the disk, our executable here goes then from the disk controller, it seeks that file and then brings it into our main memory. So we're going from here where we type in hello, and hello is stored in memory. And the result of that is the system underlying system goes, seeks that object file, that executable object file, recalls it from memory, from the hard drive space, and then loads it into our main memory. Because all of our applications have to be in main memory in order to execute. We don't execute anything directly. Our hard drive is just there for storage. It's just part of our input-output devices. It has to be translated and for us to operate through the processor. Remember, our processor has access to either memory or registers. Okay, so once we have our object file loaded into the main memory, the processor begins executing the machine language instructions in the hello program's main routine. These instructions copy the bytes from memory to the register file, from the register file to the display device. So again, we go from here to here, which would be our graphics display. It would actually show our hello world. And again, these bytes are constantly being shuttled around between these components through the buses. Okay. Let's talk a little bit about caches and why they matter. So the system spends a lot of time moving information from one place to another. The entire point of those last couple of slides was to emphasize that. For something just as simple as a hello world, you saw how much transfers had to occur between input-output devices, main memory, and the processor itself, the CPU. So in order to reduce latency, we have a variety of caches. So in our hello world program, the machine instructions in the hello program are originally stored on disk. When the program is loaded, they are copied to our main memory. As the processor runs the program, instructions are copied from the main memory to the processor. And then finally, the hello world new line character that was originally on the disk is copied to the main memory and then sent to our display device, which is then put onto our console, onto our display, on our monitor. So there are definitely speed size trade-offs for our storage. So the disk drive on a system is typically 1,000 times larger than your main memory, right? So you can store a lot more on there, but at the same time, it takes your processor 10 million times longer to read a binary word from your disk than from memory, which is why we want to load everything onto memory. The latency is ridiculous. A register file stores only a few hundred bytes of information as opposed to the billions of bytes in main memory. However, the processor can read data from the register 100 times faster than it can from memory. So to deal with the processor memory gap, systems include a smaller, faster storage device called cache memories that serve as temporary staging areas for information that the processor is likely to need in the near future. So we have this, and we start from faster and migrate to lower. So there's certain different levels, hence the term L. There's different levels of cache memory. You have L1 cache, which is right on the CPU. It's sandwiched right between our memory interface and a register space. We have L2 memory, which is also on the cache bus that can connect to the memory interface. So the idea behind caching is that a system can get the effect of both a very large memory pool and a very fast one by exploiting what's called locality, the tendency for programs to access data and code in localized regions. And if you want to get an idea of how memory hierarchy works, you can think of it kind of as a pyramid, where the higher you are on the pyramid, the quicker it is to access those binary words. But as you go down to the base, you get larger volumes of binary words that you can go ahead and store. And here, each segment shows you at what level usually that cache memory is available, whether it's at the CPU register level, or whether it's retrieved from the memory, or whether it holds cache lines retrieved from the memory. or whether it's included in main memory, or whether it's secondary to the local disk itself. So you have a variety of levels here. But really, the big takeaway that you just have to know is that the larger, slower, and cheaper storages drill down here, and that we can kind of rely on some of these higher level caching to be able to store data for us in the interim of processing these applications. Okay, let's talk about the role of the operating system. So we've talked about hardware now, the hardware considerations, about how our Hello World application runs. We talked about the software considerations, but at one point, we kind of just abstracted our software applications, just say, yeah, we sent it to the OS and it does some stuff for us. Let's talk about that OS abstraction. So the operating system is all programs that actually run on our computer system. They're serviced by the operating system. The operating system is the layer of application that exists underneath us. The operating system is a layer of software that interposes between the application level, which is what we'll now call that, and the hardware level. So all attempts by an application program to manipulate the hardware have to go through the operating system, which you'll learn much more in OS. So of course, the purpose of our OS has two primary goals it provides, values it provides. The first is it protects the hardware from any misuse and runaway applications, right? It kind of controls access to the hardware. So some third-party application, some external application can't burn your hardware out or make it crash. And second of all, it provides applications with a very simple and uniform mechanism for controlling various complex low-level hardware devices. We're going to see there are system-level calls available to us in C or in any kind of API that allows us to give instructions directly to the OS, and the OS does that for us because it's not our responsibility as an application to do that. Our applications depend on the OS having access to the hardware and the kernel and the way that everything is loaded in memory and accessible to us so that our code can do its job. So the OS achieves these goals via a couple different abstractions. We have a concept of what's called processes, a concept of what's called virtual memory, and a concept that's called files. Processes are an abstraction that includes the processor, the main memory, and our I/O device. So effectively, every application that's running in our system can be thought of conceptually as a process. You have virtual memory. This abstraction includes just the main memory and the disk I/O devices. This abstraction allows us to think of our memory as just being a big pool of addressable stuff without having to worry about what actual RAM chip we're accessing or what input-output device we're accessing, right? The OS worries about managing and pooling all the memory together, giving it an address space that we can use in our application, and then it worries about actually accessing the hardware to fill it out. So we call that virtual memory. All the addresses we use are virtual addresses, not actual addresses. The actual address is the thing the OS is concerned about. And then finally, the concept of files. Files themselves are an abstraction for anything that's an I/O device. So like, for instance, if we're reading a binary sequence that's saved on our local disk or on a flash drive or through a network, these all conceptually are files. We do file processing through input and output streams. So our abstract thing of calling anything something that's either going to come in as input or output is that file, that kind of file metaphor. Okay, and this is just a quick rundown. So as we already said, a process is the operating system's abstraction for a running program. Now, the thing that you should understand about processes is multiple processes can run concurrently. In fact, it happens all the time. Our OS is running not just our application, but multiple other applications simultaneously, and it's managing those applications as processes simultaneously. So multiple processes can run concurrently on the same system, and each process appears to have exclusive use of the hardware. So by concurrently, we mean that the instructions of one process are interleaved with the instructions of another, because they're actually executing through the same CPU. So how does this work? How can you have one CPU run multiple processes concurrently? Well, it's through a process that's called context switching. So the operating system keeps track of the state information that the process needs in order for it to run. The state is the context, which includes information like what are the current values of the PC, right? Our point counter, the register files, and the contents of main memory. So if you think about it, anything that's running at any given time, the processor has to have those states set. So it saves that. You understand that, you can keep running multiple applications if you're just resetting the states of those three things. At any point in time, a processor can only execute the code from a single process. When the OS transfers control from the current process to a new one, it performs a context switch by saving the context of the current process and then passing control to a new process. We're going to see this in practice when we build our own shell. So this is just kind of laying the groundwork so that you understand what we're going to do when we get to that future lab. So to visualize this, why don't we separate two processes that have to run concurrently, or how we context switch so that we're running one, we switch to the other, and then we switch back. So, and fast enough that you wouldn't recognize, right, when it's doing the context switching. So in our columns, we have our shell process and we have our hello process. The shell process is the application that we use to launch the shell. I mean, our hello world. And our hello process is the C code source file that we had made earlier. So here we use the shell process to launch our application code, which is going to cause a context switch to make. In fact, as an analog, you kind of think about this in the way that functions work, right? One function invokes another function, which pauses that function. You run the code from the other function, then you return back to the prior function, returning all the state from a stack where all the data was saved onto. If you understand how that function stack works, then you could think of context switching in a similar way. So we have our shell process, which we'll then use to context switch to our OS code, which will launch our hello process. And then when it's done executing, we'll do a context switch back to the shell process. And again, we have our step-by-steps here. The shell process is running alone, waiting for input on the command line. When we ask it to run the hello program, the shell carries out our request by invoking a special function known as a system call that passes control to the operating system. The operating system saves the shell's context, creates a new hello process and its context. So we have one process, which is our shell process, and now another process, which is our hello process, and then it passes control to the hello process. So it now gets the baton to be able to run using the processor. After hello terminates, the operating system restores the context of the shell process and passes control back to it. And so the transition from one process to another is managed by the operating system kernel. And the kernel is just a collection of code and data structures that the system uses to manage all these processes. That's what the operating system does. It's one of its big responsibilities that we're concerned about is process management. And then you also have this concept of threads. So in modern computer systems, a process can actually consist of multiple execution units called threads, each running in the context of the process and sharing the same code and global data. A thread is typically referred to when you have the ability to run across multiple processes. So you can have a process that has that's multi-threaded, which means that you can actually deliver your code base across different cores on your hardware. So this slide just to emphasize the difference or distinction between a process and a thread. Okay, a little bit more on virtual memory. This is a good kind of visualization that maps how we can think of memory on our system. So this is the abstraction the OS provides to us. Notice the addressable space that we have that would be assigned to our applications in the form of like pointers, addresses, would be right here. But effectively, what's happening here is the virtual memory abstraction provides a process, blah, blah, blah. Here we can see the advantages. It gives us this uniform view of memory, which is our virtual address space. The topmost region is reserved for everything in the operating system. And as we drill down lower, it gets to the point where it gets reserved for our applications. And when our applications are run, it gives us some of this addressable memory space. After it terminates, it reallocates that and then can give it to another application. This is why inside of our C code, when we create a variable, sometimes we might already have values in it, which was allocated from some other thing that it was freed up from. And so typically the regions you have are your program code and data region. You have your heap, which is your runtime heap. You have your shared libraries, your stack, and then your kernel virtual address. So you can see each of those are mapped here, 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 and here. And then finally, the last abstraction we talked about is going to be the file abstraction. So a file is a sequence of bytes. That's it, right? Just a sequence of bytes. Every input-output device includes disk, keyboards, displays, and even networks. And all input and output in our system is performed by reading and writing to files using a small set of system calls known as I/O calls. And so the reason why this motivation, this abstraction is valuable to us is it provides us a simple way of dealing with all input and all output uniformly, so that we don't have to think of using keyboard data or mouse data or monitor data or memory data in different ways. That's the power of abstraction, right? It allows us to take a lot of different granular things and treat them as a whole uniform approach. And I guess the last thing that's worth just mentioning, if we're doing this, since we've gone this far down the rabbit hole, is I want to articulate that network data is treated really no differently than any other data source or sink on our system. So the same way that we would connect to our bus to access our hard drive, or like an external, whether it's an internal hard drive or an external hard drive connected through a USB port or data from the keyboard or mouse, right? Well, we could just have right on our I/O bus a network adapter, and the way that data flows in and flows out of that is exactly the same. So networked applications are really no different in terms of the way we can manage input and output than any other kind of input-output device. So you can kind of think of the way that our system can communicate with other systems using networks as being something along the use of another application then, where you have an application that's designed to connect with another system. It creates a pipeline where it can import the data, translate it into something that's then locally available to us, feeds it into the system the way we'd expect. Then whatever output it needs to send back, it would then send to the network adapter, which the application that supports the network adapter will encapsulate that data so that it's primed and ready to be delivered over the wire, which you'll learn more about in networking. And again, this is just a emphasis on the use of why abstract models is one of the most important concepts in computer science as a whole. It's something that we not only focus on here at the OS level to go ahead and create these abstractions of files, virtual memory, and processes, and even virtual machines, but you do this probably in object-orientedness too. It's the idea of abstraction allows you to adhere to these same practices to build code bases that are represented as a collection of classes as objects that can then use composition, inheritance, and then from these modules and these packages, you can create APIs so that other developers can import, or you yourself as a developer can import into your own code base so that you can only be concerned about the things you need to solve. So abstraction, abstraction, abstraction. Computer science is learning how to use abstractions at every level of it. We already talked about the processor abstraction, the OS abstraction, and that's it. That's pretty much chapter 1. Does anyone have any questions about pretty much what it takes for our Hello World program to run effectively through a software perspective of our computer system and the hardware perspective of the computer system? Do you see how a computer system can now be defined as both a combination of software and hardware, the underlying system that allows us to do everything that we do to build applications? Because this is really the stage by which we're going to explore deeper for the remainder of the semester. And in fact, this first lab will have you exploring the 4 stages that the GCC compiler goes to translate your text source code file into a binary executable object file. Excellent. Well, let me make sure there's no questions on here, on chat. Perfect. Well, I will see you all next week on Monday. I hope to see all of you be able to have your to-do application in C.